Okay, Wang Chao, please start.
Okay, so today I will talk about the paper, the Mali Shapley value for model explanation, and it's proposed on arXiv on 2020. So it's by the two authors. Since I cannot pronounce this name well, so I will not pronounce them. But yeah, but this presentation is only for introducing the basic ideas of Shapley values, but not touching the proving part. So the two authors are all from Google, and the first author is the author for the IG, which means integrative gradient, and it's famous for it. And his area of research is mainly attribution
So
problem.
famous for IG means that he is also proposed.
Yeah, it's the author who proposed IG. Yeah, the paper is the most cited paper of all his papers.
Integrative gradient is quite famous.
Yeah. And the second author is also a data scientist in Google, and I cannot even find the image of him. And his area of research is the attribution problem. It's his latest search, and it also tried like CV and NLP. Yeah, so it's his area of research quite wide. Yeah.
Yeah. So by the way, I just Xiangling and Ruofan, you can just remember this guy's face. If in the future the vaccine is successful and the academic conference has been resumed, maybe you can meet these guys in the future conferences.
Okay. So next, I will talk about the main problem in the paper tried to solve, which is called the attribution problem. So actually, this paper did not give a formal definition of this paper. So I found this definition in one of its reference, and it is a formal definition of attribution problem. So what does attribution problem does? Wait. So what does it does? So consider. So we should first consider a function with n variables, and it's like from Rn to R. So it's from n variable to one output, and the function should be deterministic. The attribution problem is dividing the responsibility for the overall change among the variables in an axiomatic way. So what does this
axiomatic way?
Axiomatic way. So what does this mean? So suppose we have initial and final value Ri and Si. So Ri means the original R, and Si means the after R. Then we want to find a contribution such that the contribution of each.
Sorry, will you please repeat what Si means? S means.
S means the final value.
I mean output value.
No, the final. So it is comparing two inputs. So you can see here. So for S, it's an input, and we can get Fs here. And for R, it's another input. We can get Fr here. So in which
Wang Chao,
Wang
Chao, your voice is a little bit variable. Yeah.
Sorry, it's my bad. Sorry, I forgot to take my microphone. Yeah. So let me introduce it again. So there are R and S. So S are the final variable, and R is the first variable. So the problem is considering the difference between the output of two variables and attribute this difference to each dimension of this variable. For example, for R and S, they are all n-dimensional variables. And now we want to attribute the final output to each dimension of this, which is named here. So that's the attribution problem. Do you got what I mean?
I got it. So is there anyone who have questions on this definition? Okay, so maybe I raised a few questions. So have you anyone, because is there any requirement for these functions? For example, this function.
As long as it is deterministic.
Okay, non-deterministic. So keep going on.
Okay, so however, in most cases, so we only want to compare the effect of the variable. Sorry, it's something. So we with comparing with baseline value. So we can modify the definition a little bit simpler with a baseline value. And it is defined in axiomatic attribution for deep neural networks, which propose the integrate gradient. And the definition is like below. So suppose we have a function f to of n dimensional input to one vector from 0 to 1, and it can be represent a deep neural network, and an input x and a baseline x prime. So we can attribute each xi comparing with its baseline to this such vector. And each ai is a contribution of the xi with the prediction of xx. So actually the two definitions are the same thing, but replacing the Ri here with a baseline value. So there are some possible baseline values, like in CNNs, we can use images with all black pixels as a baseline. And for NLP, we may use sentence with all pads as a baseline. So that's how we can reform the attribution problem related to deep networks.
So wait a minute. So may I have an example here? Maybe we all together can think about it. How I would like to raise a counter example here. Suppose we have function. This function may or may not be a deep neural network, right?
Yeah.
So let's make this function to be A and B. So maybe I'm writing a program function here. So if A, let's write this one. If A is larger than B, then we return 0. Else, we return A plus B. Is that function fine, right? So will still have attribution. We can still do an attribution problem for this program function. Am I correct?
Yes.
Okay. In this case, according to the definition, so the definition is that given an x and xy, right? So suppose A is equal to 0, and then B is equal to, for example, A is equal to 1 and B equal to 0. And what is the attribution problem, and how do we design an attribution problem here? Sorry. So here is 1, 0. So this is x1, right? So
yeah.
This is x, and x prime supposed to be 0.
No, in this case, the baseline may not be 0, 0.
The baseline may not be y.
So the baseline value needs to be a dummy value, which will be introduced later. So if it wants to be a baseline value, it must contribute nothing to the final output. So yeah, it's may not necessary for this function that's 0, 0 to be its baseline.
If that is the case, how do we choose baseline for this function?
So we need to calculate carefully that find out x such that it will not contribute. So the Shapley value for that is 0. Then we can consider it's a baseline value. It may be a candidate, but
this function is very simple, right? This function is very simple. It's just if we look into a dimension, and suppose A, B, and F, if A is larger than B, that it will be 0. Otherwise, it will be somehow A plus B somehow. Anyway, there's a plan. It looks like this. So this is a very simple function.
Yes,
so I'm talking about how do we define an attribute.
So we can find the attribution from 1, 0 to 0, 0, but we cannot say x prime must be the baseline value.
Because I understand when Xiangling reports integrated gradient work, so the baseline actually depends on the user. So we can basically we can choose an arbitrary.
It's correct. So we can say how this 1, 0 approved from 0, 0. Yes, we can say that if we manually define x prime as a baseline.
Okay,
but
so
this once then its progress from 0, 0 may not be the true attribution of this 1, 0 to the whole scenario. So
would you please read? For example, I didn't catch your last sentence. You say this reference may not be the true one.
So I mean, we can say what. So from 0, 0 we go to 1, 0, right? We can say how this each dimension, like here and here, attribute to the change. Yeah, but yeah, that's how we define it. So if you, but this 0, 0 is just a reference point. It's not the
Yeah, I understand it is reference point. So assuming I understand there's a conditions to say how to appropriately choosing a baseline or choosing a reference. So assuming that we arbitrarily choose a reference like 0, 0. Yeah. So in this function f, and how do you calculate the attribution values from 0, 0 to 1, 0?
I will introduce later how to calculate the Shapley value.
Or maybe you can just give us an intuitive value. For example, what's the attribution of A and B to this from x prime to x? For example, in this region. Is that possible? Because this is an arbitrary function, and it's deterministic indeed.
I cannot give a very intuitive one just right now. Yeah.
But in this case, from your point of view, whose attribution is larger?
Actually, I need to calculate it, but I suddenly do not know how to apply the Shapley value on this setup.
Yeah, because here, this one is not a continuous. This function is not a continuous function, right? You can see the shape of a high value, but maybe you can keep this in your mind, and you can move on with your presentation.
Okay, but so in the setup here, then the Shapley value should so this Shapley value so actually the f0 is so fx prime is 0 and fx prime is also 0. So they are all not giving the attribution. So the attribution
and then what are 0. And what are 1, 1? 1, then this will be changed to 2.
If 1, 1, then if the function is if a is larger than b, then return 0, otherwise return a plus 1. Okay, so if it's 1, 1, then the ab in the case here, I can definitely say the attribution of each dimension is 1.
Okay.
Yeah, that's definite. But for example, it's 2a plus b, and then the attribution will be 2 and 1. That's what's true. Yeah.
So that's a baseline 0, 0.
For example, if the function is more simple, if it's fa plus b and equals to alpha x, x, how many a plus b, like 2a plus b, then the attribution will be divided by 2 and 1. But I do not know if there's a condition how to handle the value change. Yeah.
Okay. This part might be the tricky part.
Yeah. So I do not know how to handle it well. Yeah. Okay, actually, there are several ways introduced later, but I think it's better to go through the discrete one first, then to the continuous one.
Great.
Okay.
Thanks, Wang Chao. Please go on.
Okay. So next, I will introduce Shapley value. What is Shapley value then? So it is actually a concept in cooperative game theory. It assigns a unique distribution among the players of a total surplus generated by the collision of all players. So which means that, for example, there are several players, and we may arbitrarily choose each player to play the game and gain the surplus. For example, there are n players. We can choose, and we label them from 1 to n. In each game, we may arbitrarily choose any numbers from any number of players inside this n, and then let them play a game. And after game, we can get some surplus. For example, we can choose player one only, and for example, it can get the reward for 9. And then we can ask 1 and 2 play together, and it may get the reward 11. And that's how
the reward is for the overall reward or reward for each player.
It's for overall reward for
Okay.
letting these two or letting this N player play the game. So
maybe I can raise a very not sure whether appropriate example. So suppose we have a group today. We have 6 people join our presentation. So suppose we arbitrarily choosing 2 students to cooperate at paper. So we can see whether this paper can be accepted or this paper can get the best paper work, or this work can lead to a startup company, right? So if it leads to a startup company, then the reward will be 10. If it can get a paper accepted, the reward would be maybe 5. And if the cooperation between 2 people broke up, and the payoff, the effort paid end up nothing, the reward might be -1, right? So in this case, suppose we have, just raise I just think about a metaphor.
So
the player was P1 to P6. So we arbitrarily take an arbitrary number. We take an arbitrary number of people and let them cooperate, and it will always introduce some outcome or the overall outcome, right?
Yeah, correct. So it's important to assign like as an attribution or like how good a player is, right? So we want to know that among all these players, who gives the best contribution to the final surplus and who is not. So what does Shapley value do is actually calculate the average marginal contribution of each player. So before knowing what is average marginal contribution, we first know what is marginal contribution. So for example, if, for example, we have A playing game alone, we can get the value of VA. Then the marginal contribution of B joining A is VAB minus VA, which is quite intuitive, right? So the marginal benefit of B joining AC is VABC minus VAC. So the marginal contribution is what it gains minus what is not, what is when it is
just VIBC minus VAC.
Yeah, so this is quite intuitive. So what is average marginal contributions? So you may find that in the case that arbitrarily choosing N players to play, it can have many such marginal contributions, right? So we just average them and we get the average marginal contribution, which is the Shapley value. So it may not be intuitive for this average marginal contribution. So I will go to the next part, which is more clear about it. So let me go through an example. Suppose there are 3 players, and player 1, 2, 3, if they play alone, they will get 0 reward. If 1, 2 play together, they get 90. 1, 3 play together, get 80. 2, 3 play together, get 70. And let 1, 2, 3 play together, they will get a reward of 120. Now, how can we calculate the marginal contribution for each kind of permutation? So you see that on the left-hand side, there are 6 permutations of choosing N. Like we first player 1 come, then we add player 2, then we add player 3. Then this is one possible permutation, right? So if the number of N is 3, there are 6 possible ones. So actually, yeah, it's quite intuitive. It's just an ordered combination of all these players. Now, how can we calculate the marginal contribution for first permutations? You may find that after we add 1, what we get? It is 0 contribution, right? After we add 2, the marginal contribution of adding 2 will be V12 minus V1, which is 90 here. And which is marginal benefit of 3 in such permutation is 120 minus 90, right? So it's 30. So it's in the first permutation. In the second permutation, it's adding 1, then adding 3, then adding 2. So it's something like this.
Wait, Wang Chao, will you please raise a question? Next,
Actually, I will ask them to fill in the left 4, because the first example may not be intuitive. In the second example, you may find that 0 is first calculated, and then 3 is added. So V13 is 80. So we first write 80 here. Then 2 is added. Finally, we add 40 here. Okay, next I will let maybe Ruofan to fill in the 2 columns for us.
Okay.
Okay, thanks.
The next one, we Wang Chao can appoint another student to finish
so
the 3.
Maybe Yihao, are you here?
Yeah, I'm here.
Can you fill in it for us? The 2.
But I'm quite lost.
Okay, now
maybe Yufan.
Yeah, maybe
How about-
Yufan.
Okay, let me calculate.
Okay, so let's see the correct answer. So we all got correct answer. So actually this idea is quite simple, right? So yes, then we just sum them up and calculate the average value of them. So we get the Shapley value here. So now we know how to calculate the Shapley value for discrete pairs. Now we want to summarize it to one formula.
By the way, Yihao, do you have any questions about any of the value? For example, which one you're not clear?
So the arrow, what does the arrow mean?
Arrow means that first add 1, then add 2, then add 3. So it's the order of adding the players to the game. So before we only have player 1, so it can only, so the marginal contribution can get is 0 because V1 is 0.
Okay, I get
After
it.
adding 2, we get a value of 90, and the marginal benefit of adding 2 is 90. So that's how we get this and what this arrow means.
Yeah, I got it.
Okay, so understand this, we'll go to the formula of Shapley value.
By the way, that is suppose the number of data is very large, and calculating the Shapley value will be very costly.
Yeah. So that's what cannot be prevented because it's the formal definition of Shapley value.
Yeah, maybe sampling. Do you think the sampling and estimation can play some trick there?
We usually do not do sampling because actually for input features it may not be very, very big.
Okay.
Yeah, but it may also because of calculating this is expensive. So maybe that's why integral gradient is much better in the case of model because it do not need to calculate the permutation anymore.
Okay.
So next, let me give the formal definition of Shapley value, which is summarized from what we have just done. So we can see this first, this n factorial here, 1 over n factorial, which is a permutation of n, which is down here in this step. This is n factorial. And what is s factorial and n minus s minus 1 factorial? So it means so let's it means the permutation of S, the sequence before I, and the permutation of this one, the sequence after I. So what does sum up? So it's summing up, like we exclude I from N, and we subset player from this N. So for example, we just use the previous example here. Now we have, for example, so I here is 1. Then how can we calculate it? So there are 2 players now left. The possible subset of these 2, the left end is empty subset, subset of 2, subset of 3, and subset of 2, 3, right? Then we append I here, append I here, append I here. Then we apply the rest one from apart from this, like this is 2, 3, this is 3, this is 3, 2, and this is empty. Then what does, so the S here means this one, right? Then the N minus S minus I here means here, right? It's quite clear. Then why we need to calculate the factorial? Because for example, for this 2, 3 before I, it can have 2 possible arrangement, like 2, 3 and 3, 2. But in the case of calculating the marginal benefit of I, it does not matter how the players before it is arranged. So you may see that like taking here and here as an example, the marginal benefit of 1 is all same. So it just sum it up. For this N minus S minus I factorial is the same. The value, the set after it, we do not need to consider the permutation of them. So it comes here.
Okay, so we should divide them or
multiply them.
Multiply them. Okay, so get it.
Yeah. So sets and the finally is just calculate the marginal benefit of I. So that's how we can get easily from get the function easily from its definition.
Oh, I just remind you. Do you think we can apply the concept of Shapley value to the layers?
To the layers?
Yeah, because think about FYP. So layers, there's still somehow we can calculate the marginal benefits, and maybe we can think about this. I do not have something concrete in my mind, but maybe I just feel there's some potential there.
Okay, so let me go to next. Next, what is axioms? So what is axioms? Axioms are some statements that is taken to be true. However, here in the attribution problem, we are more referring to some good property that some methods holds. For example, why we need axioms? So it's because the one solution to the attribution problem should be clear, unique, and reasonable. So we want our method to solve attribution problem to follow certain kind of axioms. So next, I will show 4 axioms that Shapley value holds, which is called efficiency, symmetry, linearity, and dummy. So what does these 4 axioms mean? So the efficiency axiom means that the sum of Shapley values of all agents should equal to the value of grand collision, so that all the gains is distributed among the agents. So which means that if we using phi I to indicate the Shapley value of V, Shapley value of I for the game V, then the sum should be equal to the overall, which can be easily proved by the definition. So just
we need to add them up. We
just add all the things up, and we will find that it's just equal to Vn. Yeah, actually it's very easy to prove, but it's not hard. Yeah, so if you know some concepts of this it's actually very easy to prove it. Yeah. And the second is the symmetry of Shapley value. It says that
maybe you can omit all the proof, but you can show the examples, right? So if you go back to the previous example,
for example, you may from the Shapley value calculated here, you may find that the sum here is 120, which is equal to here. Yeah, this is Shapley value calculated, and the sum is 120, and the V123 is also 120, so it's true. Okay, so next is symmetry axiom. Symmetry algorithm. So it says that if I and J are two actors who are equivalent in the sentence that like V S union I equal to V S union J, then for every subset of N, then we have these two having the same Shapley value, which is also very clear to get from the definition, right?
So this phi I means that
the Shapley value of I of playing game V. Yeah, so that's very simple.
So here the definition V is a set. V is a set, right? V is a set of elements.
V is a set value function, which means that it takes in a set and the output a value. So it takes in a set. For example, it can take in player 1, 2, and it will output a value or the gain of the game. So it's V, or we can say it's a game because it takes n players to play and it return a value.
So I actually use the Shapley value.
So phi I
V. The Shapley value playing a V is just the equivalent to of the marginal benefits of I contribute in the game of V.
Yeah, correct. Okay, the third is linearity of Shapley value, but actually this is not related to us in the case of attribution problem because it is now considering two game function or two games. So it says that if we play if one game can be separated into two games, then the overall Shapley value should be the sum of the playing game separately. Yeah, so that is actually not related to us. So next is the dummy of Shapley value. It means that if the Shapley value of a null player in a game should be 0. So if a player is playing nothing and it's attributing nothing to the final result, then it should receive a Shapley value of 0. So it's actually something made. I have recalled that. I have mentioned that it's about the baseline value. So we actually want a baseline value that it is contributing nothing to the final output. So that's why, yeah. So that's the dummy feature of Shapley value. It says that if something or a null player is actually contributing nothing, then the Shapley value of it will be nothing, will be 0. Yeah. So why it's true, it's also easily proved from its definition because this value will always be 0, so the Shapley value will be 0. Yeah. So
let's go through about these 4 properties. The first is about efficiency.
Yeah, first efficiency, which means that all the sum of Shapley value should be the gain of the.
So I'm just curious about why it's still called efficiency. It's more like a preserving property, right?
But the name is not defined by us, right? They want to call it efficiency. So, but also it's called, but in others, I saw in other papers, it's called completeness, which makes more sense.
Okay.
In the definition here, it says completeness.
Okay, the next one is about the symmetry. So let's go through the property of symmetry.
Symmetry is that if two players can be swapped, so the contribution are the equivalent, then the Shapley value is same. Actually, it stands for another important feature. So which means so it's called consistency feature. So what does consistency feature means? Consistency. It means that if this one is larger than this for all Shapley values, then we should have v bigger than 5j. Here.
And somehow the Shapley value has a transitive feature or property. Right?
Yeah, so it means so it says that if I is always important than j, then the Shapley value of I must be bigger than j. So actually, these two are talking about the same things. Yeah. And the third is the linearity, but which is not so important. And the finally is the dummy. So actually, in the book of A Course in Game Theory, it gives a proof that Y Shapley value is a unique solution that satisfies above 4 axioms. So, so by the definition and the proving, we can show that the Shapley value is a solution that satisfies above 4 axioms. But in this book, it says that Shapley value is a unique solution. So there's no other solutions that satisfies all above 4 axioms. So that's why making Shapley value very important in the area of attributing problem, because it is kind of unique solution. Okay, so next, I will go to the part of Shapley value in model explanation. So that's why, so recall in the, it is like from binary cost sharing literature to continuous cost sharing literature. Recall the binary cost sharing literature is that the players or features in model are either present or absent. And we have a set value function which can help us calculate ES easily. However, in the continuous cost sharing literature, players or features are always present and the features are continuous. And then it comes question that how can we calculate the Shapley value in continuous cost sharing literature? And the key value is how can we calculate the VS, the set function? So now let me extend the binary cost sharing literature a bit. Recall in our simple demo, it is what we get. However, if we can view the input set as a Boolean vector of length n, what can we get?
Get a vector of 3, right?
Yeah, so we can get a vector of 3. So if now we are transforming this vector to this set vector to so now we can handle the absence of feature in somehow. So now the features are never absent, but the difference is the value is changing. So now it's original is 0, 0, 0, then it's 1, 0, 0, 0, like to indicating the absence or the present of the feature. Then if we furthermore change it to a continuous vector, then it is what we need in our model explanation, right? So suppose we use question mark to stand for a feature absence in the case of model. Then we can, and for our explicant x like this, we just need to calculate these values in order to calculate the original Shapley value. So these are quite big jump from the previous one to here. So why we need a question mark here, but we cannot use a 0? Because in a continuous settings, zeros may also stand for a feature. So, for a value. So 0 may not necessarily to be a baseline. So we have to use a question mark to model the absence of feature.
By the way, so in the previous examples, 0 means, so where you translate the set into a three-dimensional vector,
yes.
0 means the absence of certain
Feature.
element.
Yes,
So
0 means the absence of feature, and 1 means the
presence,
the
presence of certain features. But now you are saying the 0 will be if we want to.
If it is a continuous vector, then 0 cannot be used to present the absence of vector anymore. We need to use a question mark or something else to stand for that it is absent.
Okay.
Yeah. So that's why it's almost the same with the previous one, but we use a question mark to model the absence of feature. If we know how the value of each these vectors, then we can using the original definition to calculate the Shapley value, right? Then, how can we model it? So in this paper, it introduced two major directions. The first is use the conditional expectations to model the absence of feature. It's called the conditional expectation Shapley's, which is CES in short. The second is introduce a baseline value and use it to model the absence of feature. It's called baseline Shapley or B-shape. And from improvement of baseline Shapley, there are random baseline Shapley. And finally, it is the integrated gradient, which looks very different. Yeah. So let me introduce the conditional expectation Shapley first. So it mainly estimates the absence by average over samples from those features drawn from the training set. In other words, if fx1 question mark x3 to xn is so this function is estimated by the expected prediction when the missing feature x2 is sampled from data sets. Let me give a simple demo here. For example, we have data sets of f12, f13, and f22, and we need to calculate v question mark 4. Then this question mark is drawn by the probability of feature I, like there are 2, 1 here, and 1, 2 here. So v question mark 4 is calculated by replacing question mark by 1.
So here v question mark 4. So it is for arbitrary. It is for arbitrary input or arbitrary feature.
So
I think I'm a little bit confused about the concept here. Maybe I need to clarify it. So f is still a function. The next one is the feature.
Oh, f is yeah. You can see the. So f is you may recall that f is you can see f as more. You can see it's let me.
It's a gap or.
Let's rephrase it. F, the function f is. You may just think it's value, but it's
it's a valuation.
Yeah, it's an evaluation of all these x and vectors, which is the original f mentioned in the definition of attribution.
And x is a scalar or it's a feature?
Xi is a continuous feature.
It's a continuous feature. Okay. So, and when we are estimating the v is a Shapley value, right?
No, v is a set function.
Okay, so, v is set function.
But it's related to this f. For example, v if no feature is missing, then vx equal to fx. That's very clear. However, if feature is missing, then vx. So we need to calculate such value to estimate the vs.
S is a
set.
This is a set.
So for example, S here is 1. S here, for example, is 1, 2, and overall there are like 3 features. Then, which means that VS is keeping the
3 feature. How could it be? Sorry. How could it be 3 features?
Oh, okay. Then we use 2 features in such demo.
Okay.
There are 2 features. For example, VS and S we choose as feature 1. Feature 2, because we know that feature 2 is known, but the feature 1 is absent. Then we calculate this x prime with, like there are 2 features, right? The feature 2 equals to here, but the feature 1, like here, is drawn from the training data set. And in training data set, feature 1 have the occurrence of feature 1 is 1 appears twice and 2 appears once. So it just calculates the expectations of replacing the value of it, which is here. Like there are 2, 1 here, and 1 times 2 here. Then it's just replacing it. Then we we calculate the conditional expectation. Do you
But-
get what I mean?
I got it, but still have questions. And
Yes.
Under what scenario will these features be missing?
So it's what we, so just go to the previous slides. In here, it will be missing.
Will be missing. So this V stands for, example, this V, as you mentioned before, this V 3.5 etc. is just equal to F 3.5 etc.
Correct.
So it's more like estimation. So when we observe, it's more okay. So when observe some data, when we would like to evaluate or variations of a giving certain features,
Yes.
we always, given that we cannot set 0 to represent the absence.
Yeah.
So we just estimate the absence value with the average value appeared before in this location or for this feature.
Correct.
Okay.
Yeah, so that's the idea of conditional expectation Shapley. So yeah, it's quite, it's not average. So you can say it's averaging, but it's more like the expectations of replacing different different feature one here into the original xi and calculate f. Yeah, that's the conditional Shapley. And the second is baseline Shapley. So the baseline Shapley is just very, very simple. So at the beginning, we have question mark, right? Now we just find a baseline value for it. For example, we now say that the baseline value is all 0. Then we can just replace all the ones using 0 to f, and then we just calculate this f, and then we get a value. So that's what's the idea of baseline Shapley, which is simple but reasonable. Yeah, so it's quite simple, just like we use 0 to stand for a baseline, and then we calculate what is above the baseline, because the baseline value can have real life meanings. For example, if we have a picture of all black pixels, right, it can be viewed as a baseline because it conveys no information of the content of it. Then we add colorful pixels to the baseline, and then we can say that, wow, how much contribution of these colorful images, colorful pixels to the contribution of final predictions. The same is for paddings. So in most cases, 0 is a good baseline values in model, in like CNNs or NLPs. Yeah. But in NLPs, yeah, I'm not sure you guys know NLP well. So there are something called pad here. So the pad is first introduced when batching the NLP data. For example, one sentence can be 5 of last 4, and one sentence can be last 5. And we want to make these two into one batch. We need to add a pad here to keep them same, so we can run one single RNNs to handle this batch data. And if we use this pad to all the things like pad, then we can view as a possible baseline. Yeah. So yeah, that's just an extent to the baseline value. And
Okay.
and then it's random baseline values. So recall that. So first, let me introduce. It's a variety of baseline values. So but the difference is that the baseline X is drawn randomly according to the distribution D. So recall that the definition of dummy, as long as the value of Xi makes the feature I X like a dummy feature, we can view that the value as a possible baseline value. No need to be fixed. So why there are many possible baseline values? So for example, let's use an image as an example, and we only consider the feature here. For example, if there's an apple and it is recognized an apple, then the value here is actually not contributing much to the final output, right? So the value here may be considered as one possible baseline value here because it's not attributing much to the prediction of this paper. So if
that means it could be arbitrary value.
It's yeah, it can be, but so it's just distribution law. So but in most cases, some values will attribute to the final predictions, and such baseline will be very small. So the number of such possible baseline value is not too much comparing to the values, the total possible value. So we may just sample this this baseline X, and calculate the expectations instead of only using 0 as baseline. So that's the idea. Okay, so that's.
So I have a small question. So when you're talking about the Shapley value is the result of a sum, right? We need to sum up. So we need to sum up all the cases. So anyway, so there's the coefficient about sums.
Yes.
And actually it's about, suppose we are calculating the Shapley value of certain feature. So it's more like S plus I minus ds.
Yes. So what's your question?
And this S belongs to a large S. So altogether, so here.
Yeah.
And now you are talking about Shapley value of the stand. Oh, this is due to the expectation.
Yeah, it's VS. So we as long as we know these set value functions, we can calculate the Shapley value.
So as long, okay, so that means you are implicit some function over there.
Yeah, the sum is still there.
Okay.
So for example, there are 3 features here, but it's continued feature, and we just, as before, we choose the presence of, like, we first add this feature, then add this feature, then add this feature. Sorry, let's handle this way. Then we just, in the normal sense, calculate V. For example, let's say 1, 2, 3 in a number. Then we just calculate 1 question mark, and 1 V1 2 question mark, and calculate V1 2 3. Then we can just, and this question mark is modeled by this function. This question mark is modeled by this function, and we can get a value for it, and we just replace this value to it, and then calculate the Shapley value. Then it's fine.
Sure. That's quite fairly clear.
Yeah, it's clear, right? So finally, we will go to the hardest challenge part in here. So in this paper, the author, the same author as IG, says that IG is also a kind of Shapley value. So let me first give a recap of IG. Actually, it's a brand new introduction of IG because I believe most of you have forgot what IG is and how to calculate it. So let me introduce the IG formally. IG, the full name is integrated gradients, and the formula is given here. Note, we can observe a very difference here is that the IG is not calculating VS anymore. It is approximating the Shapley value from the baseline value directly by the definition of attribution problem. So it is just calculating the Shapley value as this IG or the Shapley value in this paper. They say it's a kind of Shapley value directly. So it says no more VS anymore. It's just IG. So it's also used a baseline value here, X prime. So this is like they are comparing the effect of X related to X prime. And the formula is listed here. It may not be intuitive here, so I will explain why we need to use IG and how we can get it. Okay, so how can we get IG by definitions? At the beginning, we need to recall Taylor series expansions. The Taylor series expansion says that fx plus delta x minus fx can be approximated by its partial derivative to feature I times d feature I. So which is here. This is the partial derivative of.
Can you be more specific about the delta xi?
Delta xi is a very small of it. It's very small value.
Dimension is the dimension of each delta x, right?
Yeah. So dx, so x is a vector, right? Dx is another vector, but each value in this small vector is very small.
It's an incremental vector.
Yeah. So it's dx. Yeah. So it's equals to the partial derivative of fx to xi times dxi. Yeah, that's the Taylor series expansion. After knowing this Taylor series expansions, so why we want to use Taylor series expansions? Because
I somehow forgot about Taylor extension. So this is this partial derivative fxi over partial derivative or partial derivative of f over xi.
yes.
So it's more like can be written into this one, right?
Yes, and times
Okay.
dxi. So if we recall the two-dimensional case, it will be much easier if you guys do not know multi-variable function and the partial derivative. Suppose we have one y equals to, for example, x squared, and we got these functions. And here means that, sorry, let's see, use fx to in a more simple way. It says that fx plus delta x minus fx will equals to the f prime, the gradient of prime times dx.
That is straightforward.
Yeah, that's very straightforward, right? So that's the definition. So, but what is here is just making the derivative to partial derivative, and the x are now vectors.
Sure.
Yeah, so that's the Taylor series expansions, and it requires delta x to be very small to make the approximation to be true. Then why we need Taylor series expansions? So actually, we are now attributing the delta big F to each dimension of it, right? It's a very good property because what we are doing is now.
So the derivative is just the attribution, right?
Yeah, we can say the partial derivative is a kind of attribution. So that's why Taylor series expansion is very good. Yeah, and so next, knowing that in the early stage of the IG, it's called a general Z or G or something like this. So in the early stage, before IG was proposed, they used such approximations to model the attribution of X. So we get formula equation 2. These two are actually just same, but by replacing this X plus delta X to F bar to X bar. So these two are same, but this approximation may not be accurate because delta X is large here.
So the derivative is not well, right?
Yeah. So the early stage, the partial, that's what is done here. So they use such value to approximate the attribution of each dimension. But it's recall that this is an approximation because the delta X is no longer small here. It's the early stage before IG was proposed. So so what if?
So it means you add the derivative altogether along the path, right? So that's a
yeah. However, it's an accurate approximation. So what if we can have an accurate estimation of fx bar minus xx? Then we can solve this question, right? So, so we know that if x the first order derivative of f is smaller f, then this function always holds. That's the law of integrate, right? Then suppose, as the author says that, suppose we can find a line such that the line 0 equal to x and the line 1 equal to x bar. Then we can get the following function. Now it's not approximation anymore. It's equality. So yes, let me introduce it. So in the first step, it's just replacing x bar and x by put the line function inside, and we can get this one. And now it's no longer integrating over x to x bar. It's integrating over 0 to 1. And we get this function. And then this function, by the definition of this function, we can separate to each dimension. To each dimension here. So this one equal to is just using a different way to write it. And from here to here is just what we have done before. We just distribution the derivative to its partial derivative. So now here we are not approximating, but just the evaluate of the attribution in a very accurate way. And that's finally the final formula we got. I know you guys may forget what it how to calculate the partial derivative here, but yeah, I myself is also quite lost when touching this formula, but I believe it's kind of straightforward here. Yep. So yeah, so we get this function to evaluate this value.
By the way, so here is this formula is times operation or multiplication operation.
It's actually the dot product.
Dot product. Okay. Yeah, the derivative. The derivative f over gamma alpha. And okay, the alpha gamma alpha derivative is derivative over alpha. So that's correct.
Yeah, so this is just simple derivative calculating. Yeah. And then, so we got this formula. And the author in this paper says that, so that's we got the attribution for individual feature I as listed here. And the author says that for this line, we can just use a very simple line using this line here. So which means, so this line means just a straight line between x and x prime. Sorry, x bar. So that's also a very simple line. So let me say that, for example, there's a dot here and a dot here. The easiest way is just like, yeah, this is a line function here. So this is a straight line between this one. And this, you may just replace alpha equal to 0 and alpha equal to 1 here to see if alpha equal to 1, then x bar. Then alpha equal to 0, then it's x. So it's actually modeling a straight line between two x. If we replace this this line here in original function, we know that the derivative, so this one can be calculated easily because it's just so this one can be calculated easily, which is this one. And then replacing it, we just get the final IG formula. So this one, we got x and x prime swapped for x and x bar. But yeah, it's just the same here. Yeah, it's a very long.
It's a induction. So I enjoy the inductions a lot. So have you prepared a question here? I think the questions can allow us to.
So maybe Xiangling can answer this question. Why is this one why is this one equal to this one, given the line here? So it's a math question.
So you just calculate the.
So we are calculating
the
gamma alpha over dxi.
Oh, alpha. I think it's
dd alpha. Sorry, dd alpha. dd alpha. Yeah.
So just the formula of derivative, right?
Yeah.
Just apply the formula of linear derivative, and you will just got it. Just got it.
Yeah, it's quite simple, right? So yeah, so we just got this. We can just get this IG formula from the definition of the extension of, so using equation to model it. Yeah, that's how we get IG. Okay, so hopefully all you guys know what is IG now. So next it comes says why the paper also introduced why IG extension of Shapley value. So this one actually myself cannot understand the logic, so I leave it here for reference. The reason is that they do not give a formal definition of what is reward, work, and pass. So I can only guess what they are trying to say, but cannot judge their proving is correct or not. So let me help. I'll just use an example here to guide you guys to walk through his explanation of why this IG is an extension of Shapley value. So let me switch to later. So it also says that it's less clear how this IG is an extension of binary Shapley values. So IG traverses a simple smooth path between the baseline and the explicant and aggregates the gradient across along the path. So first, in the left point is a two-dimensional settings, and this is baseline X, and this is applicant. The applicant X. This is the baseline value X prime, and this is X. And what IG do is here. So it traverses through the the smooth line to its diagonal. And what usually Shapley value do is traverse two lines. One line is here, and one line is here. Do you guys got question of why this one line is lines like here? Because we only model the variable goes from off to one or to on in one shot. So here we have feature on dimension X on, and then we have feature for dimension Y on. So we got this path. And here we got a feature for dimension Y on here, and got the feature for dimension X on here. So there are two jumps here. And the Shapley value is just averaging of two paths here. But the IG is over here. And it says that we may partition, so now if we extend to n-dimensional case, the IG can be viewed as the internal diagonal of this n-dimensional hypercube. So now it's a square, but you now imagine it's a 3D way, then it's a diagonal, and it's a hypercube, then it's also diagonal. But in the contrast, the Shapley value is average over the external path over the edge of this hypercube. So maybe I can draw ways to draw something for you better understanding. So suppose we have a cube here. So now it's three-dimensional, right? So what is IG calculates? For example, this is a baseline and this excipient. So it just send me over this line, right? Or maybe my drawing is too small, so maybe maybe I can draw a bigger one. So it says that IG is traversing this one. Then what does Shapley value do? So actually it is traversing through all its external passes over the edges. For example, we can have, this is one pass, this is one pass, this is one pass.
But they will calculate an average, right?
Yeah, they calculate the average of them. I'll talk about how they calculate this average, handle this average later. And this pass. So actually, it's just a permuting of all features. If you view the three dimensions as three features, right? So it's calculating the external pass, which is external pass over the edge of this hypercube. Now, the author says that if suppose they separate the features into m micro features, where each micro feature represents a discrete change of feature of value from here. So now in these settings, we are now like making it splitting it into micro features and micro features here. It says that if we apply Shapley values on those n times m features, it's equivalent to create grids inside it. So we have some grids inside it, and then we go through a random monotone walk. So for example, there's a possible walk is like this, it's like this, like this, like this, and then finally walk through here. And another work may be like this. For example, here. So if we participate, there will be many kind of these random walks here. And it says that if M increase, the density of the random walk will converge to the diagonal of hypercube. So it says that if the M is small enough, the random walk will be converged to this line here. And then, so it says that running Shapley value on those micro features is equivalent to running IG on the original feature. So that's how they explain it. So I know it's quite hard to digest. Actually, I like spent 2 or 3 hours trying to understand what it's meaning, but I cannot get it. Yeah, but I just can repeat what they say to you and make it more understandable, maybe.
Yeah, I think you did a good job here.
Yeah, so that's what they say. Why is this extension of Shapley value?
But according to the Shapley value definition, it will be very, very computationally expensive.
Yeah, but use IG,
Right.
it's quite, so it will be
It's
much
more like a shortcut. It's quite a shortcut.
Yeah, but actually IG, so the calculation of IG is also expensive because we cannot do integrate directly on the
Yeah, we still need to
different
divide it. We still
Yeah, we
divide the
still-
parts,
yeah,
give it a parts,
right.
and try to sum it up. So
Yeah,
that's
correct.
formula.
But comparing to the permutations operations, such ways is already very cheap operations. And then, okay, that's what I just go through here before. So actually that goes to the end of my presentation. So so I just introduced different Shapley values can be used in model explanation. And I did not even touch the core part in this paper, which they also prove the some axioms on the the conditional expectations. Let's go through this page. So actually in so actually in the origin paper, it also shows using some examples to show that this one do not satisfy the dummy property and the symmetric property, and all these three it satisfies all the 4 properties. But yeah, understanding it itself is quite difficult. So I will not go through why they satisfies all these properties. But we just know that in this paper they discuss the advantage of these 3 methods over these methods. Yeah.
But I have a small question here.
Yeah.
Do they mention ACE, the average causal effect? Because I think there is some similarity between the conditional expectation and ACE.
Yeah, ACE you still need to sum it all together, right? Still sum all the rest of the cases together,
Yeah, so,
calculate an average.
Yeah, I think they are quite similar, right?
No, I didn't look through the details of it because the PDF you sent me is quite long. Yeah, so
I think the Shapley value is actually a very good measurement. It's very good measurement for us to use. It's basically the tool for us to think about it.
Yeah.
And there will be.
Also, this paper also says that there are infinite number of paths. Oh, sorry, it's not paths. Infinite number of solutions to of Shapley values in the case of continuous settings if we do not add more axioms to it. So if we only have these 4 axioms, there are infinite number of solutions. So these all 3 are kind of possible solution to it. If we do not need the method to follow more axioms. Yeah, that's also the paper also prove that. So you can see that I introduced so many different Shapley values. They are all valid Shapley value in the case of all 4 original axioms. Yeah. And the paper also introduced more axioms and how they is in that paper. Yeah. So more details you can find by yourself in that paper, but I personally do not recommend you to do so unless you want to be an expert of that area because it's quite hard to understand. And you need to refer to other papers when reading this paper. Yeah, that should be all for my presentation.
Thanks, Wang Chao did a very good job for presenting. Even the paper I think is very difficult, and I really enjoy the talk. Thanks, Wang Chao. Let's move on to the next one. Who's supposed to be Yihao, right? Hello, Yihao, are you there?
Me.
Oh, sorry, Yufan, sorry. My fault. Hello, Yufan. Yufan, will you please share your slides? So Yufan is going to provide a survey of machine learning used for code and comments. Usually, there's so Yufan's PhD work is more towards NLP. So his focus is on to learning representation. For example, for computer vision, we are focusing on how to learn a representation for images. And for the natural language processing, we will learn how to learn a valid or useful representation for a sentence or a word. If a word is a very famous word embedding there, and Yufan's work is working to code, and whether we can have a very good embedding of code, and whether we can build a bridge between code and natural languages that they share the same embeddings. And if we are successful, we are likely to make the contribution to translate code to comment and comment to code as well. Okay. You can please start.
So today I will present the paper, A Survey of Machine Learning for Big Code and Naturalness. It is published on ACM Computing Surveys in the 2018. And there are 4 others. The main other is Malthus, Allamanis, and these 3 guys are professors, and there are some relation between them. In 2017, when the title of the NLP paper is "Attention is All You Need," the paper of the programming language is "A Deep Neural Network, the Best Choice for Modeling Source Code." And this professor put forward a question called "Out of Vocabulary," and you can see that in that area, deep neural networks seem to have some problems. But in 2019, this prof gave a paper called "Maybe Deep Neural Network are the Best Choice for Modeling Source Code." He put forward a neural network system based on an open dictionary which solves the OOV problem. So, so these professors have some relations and debate on this
argument. So they turn from the enemy into the friends and force us to propose this survey, right?
Yeah. And then we talk about our his paper are mainly focused on the relation between the code and the natural language. In 2013, he just built a probabilistic language model by Java. And in 2014, he just built a recommender for variable name, and 2015 for class and function name. And because of the trend of machine learning and neural network, in his later work, he just focused on the convolution, attention, and nowadays the graph neural network to code representation or code generation. Okay, so back to the survey. If you do not follow the research update in this code natural language fields, maybe you are not able to understand this paper easily. This survey is more like to tell you some experience or some rules in this field. And first, we need to understand the title, the machine learning, the big code, and the naturalness. First, in this paper, they think the promise and the power of machine learning rests on its ability to generalize from examples and handle noise. They think that the machine learning is more like black boxes to replace heuristics and find some features that are not defined by human. Just as natural language processing research changed focus from the brittle rule-based expert system that could not handle the diversity of real-life data, they think soft engineering and the programming language should also make the same transition. That means from the traditional methods just consider formal structure and a very detailed and subtle mathematics. They think that nowadays we should use more about like statistical properties of code. And what is big code? Nowadays, open source software system like the Linux, MySQL, and many other open source code, this system just gave us a very big treasure to mine. I think it is just like big data and data mining. The scale of the available data is massive, and the billions of tokens of code and the millions of instances of metadata such as changes, bug fix, and code reviews give us chance to find the statistic rule behind this code. And on one hand, the code contains may contain some statistical properties, and on the other hand, the large and the typical software and the open source also influence our programmer to copy and learn these styles. And finally, what is the naturalness? The naturalness hypothesis, it comes from this paper, and these two professors cooperate on this paper. And as all the language we communicate in the daily life are very repetitive, regular, and predictable, so they think as software is a form of human communication, software corpus have similar statistical properties as natural language corpus. So these properties, these statistic properties can be also exploited and to build better software engineering tools. And in this paper, they just prove the code is not only natural. That means not only contains static properties, even better than the natural language. I think this is big. Follow this paper. There are many language model, and there are many probabilistic code models to develop these fields. After there have many new probabilistic model for code, there also give many new tasks like the recommender, like code completion, or like summary bug fix, like these new tasks. And I think some tuition behind the hypothesis is that the developers prefer to write and read code that is conventional, idiomatic, and familiar because it helps understanding and maintaining software system. Okay, so this is the understanding of the title. Now we trying to understand the contribution of this paper. First, the paper introduced some relations among text, code, and machine learning. It is a very long survey with 40 pages. It talks about many parts. So we just focus on these three contributions. The first, what's the relation between the text, code, and the machine learning? The first is bimodal. That means code communication along two channels, one with humans and one with computers. Humans must understand code to read and write it. Computers must be able to execute it. The bimodal of code drives the similarities and difference between it and the text. The most difference is that code is executable and formal. Executable means that code is often brittle. That means small changes can drastically change the meaning of code. And you know, the natural language is more robust because we can understand text even if there contains some mistakes. And in addition, sensitive of code means that we need to combine probabilistic model and the formal rule-based methods. Nowadays, the existing works is also focused on builds probabilistic models and apply strict formal constraints to filter their output to make the code executable. And the others of this paper think further research may be focused on bridging formal and probabilistic methods. And so for formality, programming language are designed top-down by a few designers for many users. And natural language, in contrast, is emerged bottom-up, like through some social dynamics. And in addition, natural language changes gradually, while program language maybe have some punctuate change, like Python 2 and Python 3. Besides, text has a robust environmental dependency, while code is very sensitive to the environment. And this formality facilitates the reuse. That means one can maybe find thousands of new articles, but the code is more like copy from each other, like a pattern dense than text. Because programming language are automatically translated into machine code, they must be syntactical. And the fifth is that cross-channel interaction. Some code have natural semantic units, like our programmer always want to name the function a meaningful name. This is explanatory channels of the code. And finally, for the path tree of sentence or the text could be diverse and very short, because our sentence will no longer than like maybe 50 words. And the tree will be much more shallow. And the path tree of code, in contrast, will be much deeper with repetitive internal structures. Okay, so this is the relation and the difference between the text code and the machine learning. Any question for this part?
Yeah, so I think it's good to show the difference, but is there any more summarizable or examples for us to digest? Maybe we can move on. I understand. So please, maybe
because
you just take it from the paper. But we can keep move on. By the way, to the presentation, we expect examples.
Okay. Okay. So the next part is I will introduce some probabilistic models of source code. There are three types. The first is code generation models. You can just analogy to the models just like the NLP models, language models like GPT, BERT, or other machine translation models. And the representation models of code is just the code representation learning. It is like the named entity recognition, text classification, and sentimental analysis in NLP. For the pattern mining models, because the time limits, so we mainly focus on the formal 2 models. For the pattern mining models, I will just introduce it. First, the code generation model. It defines a probability distribution over code by modeling the generation of smaller and simpler parts of code, like the tokens or the AST nodes. For the formal definition, if given a data set D and the code representation R, maybe we can have a context of the code. The context of the code, maybe the context of code maybe will be none, because we don't have a context, or we will maybe it's just the natural language. Then this task will be text to code. This is transfer learning. And for the model, it always predicts the P based on the D, based on the data set, predicts the code representation and based on the context of the code. This is just a general formation of the code generation models. And for details, there are 3 categories of generating models based on the way they generate code structure. The first is token level models that generate code as a sequence of tokens. So for these models, it just follows the NLP model. And for the syntactic models that generate code as a tree, so you can see that it's just use the AST tree. And for the semantic models, it just generate graph structures. We go to details. The token level models view code as a sequence of elements, usually code tokens and characters. We can just follow the NLP models because sequence-based models are very common and because they are very simple. They just view code as sequence of elements and predicting a large sequence in a single step is infeasible due to the exponential number of possible sequences. So there will be like Markov chain and the Markov assumption. If you are interested in it, you can refer to the NLP models. For the syntactic models, they are mostly focused on the abstract syntax tree, AST tree. They describe a statistic process of generating tree structures. And this model just simplified assumptions about how a tree is generated. Usually follow just start from a root node and then sequentially generate children top to bottom and left to right. Okay, so for the syntactic models, it's always computationally expensive because you know, the variable shape and the size of the tree. I just said the compared to sentence syntax tree, the code syntax tree always very deep and have some repetitive components. Okay.
But that does not explain why this computation is expensive.
Because the tree will be very deep.
But the sequence can be very long.
I mean, compared to natural language, because natural language, the sentence will no more than like 50 words. So the tree is
but like the code. But the problem is we're talking about the code generation. The sequence will definitely longer than 50 tokens, right? So if we would like to generate a piece of code, we might need to synthesize a sequence more than 200 or 500 tokens. That's all possible, right? So how could it be the tree-based technique is more computationally expensive than the token-based approach in terms of generating the code?
Yeah, in the paper, it's just compared to the natural language models. It's not compared to the token level models. But for my understanding, the token level models just from one, maybe I write. Because of the Markov chain assumption, when you predict the m, you just focus on the m-1. So this will be much easier if you have some simple assumption. Okay. Okay, for the semantic models, it focuses on graph models that can generate the graphs. Graphs are natural representation of source code that require little abstraction or projection. However, graph model is also very hard because there's no natural starting point or generative process. And there's only little literature in this area. So the future may be on this path because of the graph neural network. The main other also write a paper about graph neural network in coding. Okay, so here is more literature for generating code. This paper gave us a very comprehensive table. If you are interested, you can refer to this table. Okay, so after the generative models recapitulate the process of generating code, code representation give example representations, including token context or data flow. The resulting mode want to yield a conditional probability distribution over code elements properties, like the types of variables. Research have built models to learn intermediate, not necessarily human interpretable embeddings. Maybe just follow the idea in natural language, like a vector embedding of code. So the main focus of the code representation also copies the ideas from the natural language.
By the way, can you show me again about the graph representation? So generate a graph. And for this graph, because even if it is a graph, it's very hard to synthesize the code, right?
Yeah.
So the graph you here, have any papers on graph? So do you know what kind of graph models are used in existing literatures?
Up to now, I only read this papers mean other. Allamanis, he writes a paper on using the graph neural network to generate code.
But the graph network is just compensates some structure information. It is not necessarily.
No. Some graph neural network are used to generate. There's many different.
I understand. Graph neural model can provide information to, for example, for Yihan's work and now generating comments. We're using graph neural network model to synthesize comments, right? So I'm talking about now here what it means is that the output is not a, just like in your previous slide, the output is a token sequence or a tree. But now the output is the graph, right?
Yeah.
And what graph are used, what color graph are used to represent a code? And how do they transform such a graph or such a structure into the code? So that is my question.
Yeah, it's only focus on the like data flow graphs and the control flow graphs.
But control and the data graph cannot be reversely generated code, right? When we have code, we can have data control flow graph. But when we have data control graph, we may not necessarily synthesize a piece of code.
I'm not don't
okay.
know
So if you do not answer, we can keep just moving or just move on, and then maybe we can quickly summarize the takeaway about these surveys.
Yes, for this part, it only have one program that's introduce some tasks that using the graph model to predict like data flow graphs or control flow graphs.
Okay, that's fine. Let's keep going on to see. To keep going.
Okay. So now we talk about the representation learning for code. We just can copy the idea from the natural language. There are two types. One is distributed representation. It refers to arithmetic vectors or matrices where the meaning of an element is distributed across multiple components. So it's just the idea from the NLP using the like BERT or like ELMO to get the embedding of code. And for the structured prediction, the second part, okay, sorry. The second part, structured prediction is the problem of predicting a set of interdependent variables. A simple example in NLP is part of speech predicting, like predict a part of speech tag for each word in a sentence. So you just can think it's an idea from NLP. So structured prediction is particularly well suited to code because it can exploit the semantic and the syntactic structure of code. Okay, so from my perspective, I think the idea for representation learning for code are all copied from the natural language. So you can understanding by the viewpoint of natural language. Okay. So for the pattern mining models, aims to discover.
Yeah, I just have a comment for the presentation. So we go through, when you are going through that, you will have a lot of I don't know because I didn't check the paper content, but when compare your talk with other people, other students, apparently your slides lack of examples. For example, when you prepare a few presentations, what the presentations look like. Otherwise, we can gain very little information from your introduction. So here, I think because a lot of students take time to join your talk, we would like to have something substantial. Something substantial means that we can have something we can take away. So in this example, I understand you paid the effort, you read the papers, and based on your introductions, you prepare slides for each paragraph, especially in the introduction part, if I'm correct. But anyway, we expected it. So when you go through the slides, I just feel that I get very little information. So in your future presentations, I suggest that when you're giving an argument, you provide an example, unless this argument is fairly easy to understand. And for now, for example, giving these slides, the structured prediction, using the predict a set of independent variables, right? So people interdependent variables. So how this will be helpful for certain applications, right? And how the task is designed. So we would like to know this kind of information. And also when you are looking into this, reading this paper, looking into the details, the technical details, it is better to summarize their ideas, to think about how to feed these ideas into your own PhD research. That was the most important part for us to read the paper. Otherwise, reading paper will not bring us more benefits. So in your next talk or presentations, you can just quickly go through this one slide by slides. And if your slides, this one slide you feel is less informative, we can skip these slides. No need to write it apart. But just keep move on.
Okay, so I just give example, like for this distributed representation, it's just like you can copy the idea from the bird. It just gives the embedding of the code, and the training method is just as I talk about the code bird. So I think because there are many papers about this, so I think I can only give some examples I have read. So for structure prediction, I think you can just copy the idea of part of speech prediction in natural language. That means like for every word, it has a part of speech. Maybe like this is a verb, predict, this is a verb. Okay, so this is a noun. So for structure prediction, it just predicts the part of speech. For code, it may predict some maybe other information, like this is a variable or this is a keyword, like this.
But do you think it is necessary for applying structure prediction on code? Because the code needs to be compiled. If a code is compiled, the compiler has already know all the information of AST tree. So each code fragment can corresponding syntax, right? In the syntax tree. So why we bother to predict which one is variable, which one is keyword? The compiler know everything.
Yeah, but I just give an example because I copy because I just want you to know what is structured prediction, but the actual process of structure prediction in code, I'm not very familiar with it. I don't know because the paper also gives some examples, but
okay, let's keep going, and then I will help you to find the focus. And once we say something interesting, let's have a discussion. And otherwise, we can skip some of the slides, I think.
Okay. So for the pattern mining models, we can, the example is that you can just follow the idea in data mining. There are aims to discover a finite set of human interpretable patterns from the source code without any annotation. That means it is unsupervised and present some maybe like minor patterns to facilitate software engineers' task. So this model is focused on to mine some like patterns in the code to facilitate the task of software engineers. And I'm not very, don't know about this part of job, but I only want you to know that this is a part of data mining task. Okay. Any question? Okay. So here is a literature for this part. Because I'm not familiar with this part, so I give you the literature. If you are interested, you can refer to this work.
Let's keep going. So something is very straightforward.
Okay. So now we have finished the probabilistic models of code. Here are 3 types. The first is the code generation models. We talk about based on the tokens, based on the AST trees, and based on the graphs. And for the representation models of code, we talk one is like the part of speech, and the one is like the bird just train the code to give a embedding. And so the pattern mining models, I'm not familiar, but what I get is that it just use the unsupervised method like the data mining, like you can cluster some code to get a very common pattern of code. So here the example may be a cluster. Okay, so now we going to the final part is how to adapt machine learning models to applications. This paper gives 8 applications. We will go details about the code to text and text to code and the program synthesis because these 2 parts are related to my PhD. I will just introduce other application. Recommender system make recommendations to assist software engineers tasks such as code auto completion, code auto completion, and recommending likely code reviews for a given code change. And probabilistic reasoning is well suited for inferring intent, since it allows us to quantify the uncertainty that is inherent to infer any latent variables that will give the code combination and recommend a good representation.
I think let's keep the rest of the part code effects translating factors. Let's go straight forward to point 5 and 7.
Okay, so this part, okay. For the code to text and the text to code, this job has many useful applications, but there are many challenges. The paper lists 4 problems. The first is the diversity of both text and code. I think you can understand it, so I didn't prepare an example. And the ambiguity of text, maybe like the ambiguity of text, I think because now
you can just keep going. I understand. Let me ask you, if you go through those points and I focus on another questions, what is compositional nature?
So if you don't understand, you can just ask. And the third part is the composition nature of code, and the fourth is the layered abstraction in software.
So I'm asking, what is compositional nature?
Oh, that means that the code is very complex, and
okay, got it. So so compositional nature is more like the code sometimes. For example, the method will call a method will call another method, and for code, there actually there's a for loop, or there's a nested loop or nested if structures for the code. So that will be not like the natural languages. The code will organize the elements in a more organized logic.
Yeah.
Okay, so can you raise an example? So raise an example of layered abstraction.
No, I can't. I didn't understand this part. I actually don't very understand these 2 parts because I'm not familiar with how to build a software. For my understanding, the layered abstraction maybe means that it has some rules. You need to control the software in a certain environment like this.
I don't know now. If you don't know, I suppose I will have some confusion as well. So the layered abstractions might mean the object detection. So sorry, the object-oriented programs. So maybe they have different layers, the different layer of the superclasses, interfaces, structure if you are using Java. We'll keep going on. So anyway, somehow there's something. Please go on.
Yeah, and the paper just lists these 4 problems, but it don't give the corresponding solutions. And
okay, keep going on.
So it only lists some literatures for like for code to context. It gives 3 examples like.
Keep going on. These three lines provide an information there.
Yeah. Okay. For the text to code, it is related to semantic parsing in natural language processing. What is semantic parsing? Semantic parsing is a task that converts a natural language utterance into a representation of its meaning. So it's just like have a latent vector of a text. You get the meaning of the text, and then you represent the meaning as the vector. This area has attracted growing interest with applications such as converting natural language to Excel, Java expression, shell commands, and simple if-then programs and regular expressions or SQL queries. And this guy presents a neural architecture for general purpose code generation. So you can see that the previous focus mainly on some certain domain, and nowadays we can use some neural networks to have general purpose code generation. He also gives us a survey of code generation methods on text to code fields. Okay, so that's all for the code to text and text to code. This is now we're going to program synthesis. For example, here I give an example because I also don't know what is program synthesis. The program synthesis is like this. You give the formal 3 pairs of input and output, and the program will give you the later 3, the words in gray color. So it's just it's a bit like code completion. For the formal definition, program synthesis is concerned with generating full or partial programs from a specification. So what is specification? Specification is the formal statement in a logic. Sometimes it may be partial or incomplete. In this example, this is the input and the output pairs. Sometimes it may be a natural language description. So for my PhD, maybe I can try to focus on using just a natural language description to program synthesis. Okay, any question for this example and the program synthesis?
Please go on. Please go on.
Okay. Here, the paper thinks the core challenge for the program synthesis is searching the vast space of possible programs to find one that complies with the specification, the certain specification. Probabilistic machine learning models can help guiding the search process to have to get a more probable program. So that's the 8 application for the probabilistic model of machine learning in this area. That's all.
I'm not sure whether the problem of the paper or the problems, or maybe the problem of my selection of paper, or your presentation. So I suggest that I think you can learn a bit from Wang Chao's presentation. I'm not sure he's still there, but you will find that when he was conveying ideas, we do not follow the template. We follow our mind, follow our heart, and we express an idea and we try to echo our mind so that the idea is thought-provoking and it will trigger us to think about it. And for this work, I understand it's a little bit difficult to present a survey paper, but I think one of the, so it is not like the high school students or anyway students, we prepare slides for scores. No, the meetings or group meetings here is that we convey idea, spread idea. So you can think about it that we come here to spread something new and novel, and sometimes we sparkle the new ideas during discussions. So I'm not saying that the presentation is not good. I'm saying that your presentation can be more vivid if you provide more examples, organize the material in terms of stories. And for example, this is a survey paper. So what do you think? The takeaway points? What is the takeaway points from the paper, and what do you learn from the paper, and what do you think the most appreciable points you got from this work?
Because this is the survey, so the main contribution of this paper is to introduce different tasks and introduce this field to you. I think you can just understand we just talk about the code generation models, and there are 3 types, and how they work, what's the assumption of each model, and the application, and the application means the code.
Okay, my question is that what have you gained, or what have you learned, or what is the most valuable points you learned from this paper?
I think I just have a whole understanding of this area. I know what point or what field people are want to research, and which part maybe that this part is very promising and have a good future.
Okay, so maybe you can just ask a few minor questions regarding how well you understood the paper. So giving your point for the copy and the clones, and how does the machine learning approach can support the copying and clones?
Pardon, please. I think maybe some wrong with my earphone, because I always don't get very clearly about your meaning.
My sound or my point?
Yes, your sound, because it always stop and continue, stop and continue. So
I'm asking that when you're talking about the copying and the clones, and how the machine learning, the copying, the point for code translation, copying and the clones. You see your slides?
What is copying and the clones?
Clones.
Oh.
Your point 4.
Okay, the copying and the clones. You mean this part? This part is mainly focused on how to translate one program language to another code program language.
What about copying? So this is for translation, asking the copying and clones, and how the machine learning can support this part.
Because for copying, it always focuses on the representation of code. That means it represents the different language of code with a certain embedding. That means that means let every different language of programming to a certain space. Then you can compare.
I have to interrupt you. You made a good try to make up a story, but I guess it is not true. So if you don't know, just don't know. Do you think what you say is that it's conform to the paper, or do you think when you made up, do you think that's according to the fact?
I think it's from paper.
Okay, you open the paper.
Okay.
Let's look at the copy and clones. You say, let me repeat your point. You're saying that you learn the same code representations from different program language. Am I right? So that's what I'm saying. Okay, please share the paper.
Okay.
You need to reshare the screen. We need to reshare the screens, and now
do you see the paper?
No, we can only see your browser.
Okay. Could you see it?
Yeah. Let's go through copy and clone.
Yeah. You can see that
this code translations, I'm asking the copy and clone. It should be supposed to be the last paragraph, right?
No, actually for the every application, it only have one part, only a small part.
Yeah,
so,
the first, we can see the first, there's 3 paragraphs. The first is code translation.
Yeah.
The second is copy. And I think the first 2 graphs is about the code translation, right?
Yeah.
And
the
last graph, the last paragraph is the last paragraph is for clones. And how does it relate to the translation?
It's not. Here is the existing research, and here is the like how to use the what is the challenge and the problem of the current model. So
you can look at the last paragraph. How does it relate to the support the same representations of multiple program languages? And how does your point fit according to the last paragraph?
Yeah, I just read some like this, like use auto encoders and recurrent neural networks to find clones and code space that share similar distributed representation. So I think maybe it's just like let all the code snips to a certain space and try to find the similar vectors.
Okay, so here, but it's very different from about the representations of different program languages, right? Copy is just a copy a piece of code in the same project. So the copy, if we think copy code, it's very hard to copy a piece of Java code into Python. It is not. It is quite counterintuitive, right?
Oh yeah, but I think maybe the code representation is the general task, because if you want to code generation, you must use a good way to represent the code. So I think
I'm asking copy and clone. So whatever it is. So in this piece of code, give me your presentations. I think we kind of short of time because it already take more than 2 hours and close to 3 hours. So I suggest when in the future presentation, because we will have another paper arranged for you. Have you noticed that? So we have another paper arranged for you next week. So I suggest that you fully digest the details and prepare examples and organize the stories. And having a very good presentations, I think it is of essential, it's of paramount importance to in the process of PhD training. So I suggest you try to start with examples.
Okay.
In your next presentations, you're trying to follow a skeleton like why we need this, why we need such a technique, and what problems are we going to solve, and then you follow up with example on how the technique can address the problems and why it can overcome the difficulties or technical challenges of the other approaches. And your presentation, your paper in next week is proposed by Hu Kaiming, who is a very famous professor in MSRA. So we expect that you can have a more prepared presentation for that paper.
Okay, so I have a question: how to present a survey with why? Because a survey is more like introduction. It's just introduce what, and introduce the concept. It don't give you why you should why you should define as this way and why you give this task. So
you can consider survey is actually a knowledge graph. Survey is actually a knowledge graph. So when we provide surveys, so they will class people and the researchers or the authors will have to classify the literatures according to different criteria. Then they make a comparison between these surveys. For example, suppose you're an expert, I'm not sure. Suppose you're an expert in badminton, right? So you will somehow understand, or you're an expert in animes or Japanese manga, whatever it is. So you always keep a knowledge graph about who is the most updated versions, and who is the best seller books. So which authors actually publish or having the waves make up the best story. So you have something in this mind. And in these surveys, a good survey always provides insight to gain these knowledges in the shortcut. So somehow, if you convey a survey, you somehow start with a set of problems. So what problems I'm going to address, and what this problem looks like, and who is the most famous authors in these areas. So that is basically a very important knowledge graph for researchers if they want to enter this area.
Okay, actually, my examples is from this paper. This paper also gives some examples like the cluster or like some models compared to natural language, because the main other is focused on natural language originally. So it's just a copy many ideas from the natural language.
Actually, a survey paper can hardly be considered as a collection of abstraction of other papers. They will hardly consider a survey. A survey usually provided a very good organizations and provide a good architecture, and they group a set of papers together. And this survey, why you assign you survey, because this survey can also provide a good material. Not only to start up, when you write a paper, a lot of reference work can come from this survey.
Yeah.
Okay, I think let's call it a day. And thanks everyone for attending. And thanks Wang Chao and Yufan's presentation. Bye everyone.